Okay, beginning of chapter 5. This is an interesting chapter, and if you had already had that through with Mr. Hill, there's probably not one you remember fondly. Sorry. It's called analytic trigonometry, and it's all about looking at relationships between the 6 trig functions, their graphs, and combinations of them, and things like that. Anyway, there's a little blurb there about those penguins you see on that page. I'm not sure we want to read that. You could if you want. Anyway. I do like the chapter 5 overview. I always do, because it kind of tells us where we're headed from and reminds us where we've been. So if you want to look at page 444, we're going to read this together. It says, although the title of this chapter suggests that we are now moving into the analytic phase of our study of trig functions, the truth is that we have been in that phase for several sections already. Once the transition is made from triangle ratios, which you learned in geometry, to functions, that is the curvy things we've been graphing and looking at, transformations of, things like that. We move to actually graphing them as functions. One has already stepped on into analytic stuff, okay? But our primary applications of trigonometry so far have been computational. You have to calculate it again. We have not made full use of the properties of the functions to study the connections among the trig functions. You're going, why do we have to do that? Oh boy, knowing these relationships and how to work with them is imperative to your success in calculus. In this chapter, we will shift our emphasis more toward theory and proof. Ooh, every math teacher or student loves to hear that. Exploring the properties of these special functions lead us, often with no immediate concern for the real world relevance at all. So if you're expecting this to apply to the real world, it's going to. Don't expect it, it's not going to happen. We hope in the process to give you an appreciation for the rich and intricate tapestry, he's waxing poetic here, the tapestry of interlocking patterns that can be woven from the 6 basic trig functions, patterns that will take on even greater beauty later on when you view them through the lens of calculus. That's what he's trying to get at. This is a pre-calc book. You're going to have to know how to manipulate these things and write them in different ways, and you have to be able to be competent at that in order to write certain things having to do with integration, for example. And recognizing when you have an identity after you've done a derivative. It's all coming into play for calc. And if you're never going to take calculus, then you have to learn this anyway. I'm sorry. Okay. All right, identities. And I would go through this whole thing about identities. If you really want to, we can. It kind of links algebra with the trig, but I think you're all sharp enough to figure this out. An identity is something that's true no matter what value you plug in. Always true. Maybe I'll just touch on it a little bit. Look at number 2 in the identities of that page. It says 2 times x minus 3 is the same as 2x minus 6. Can you see that by distribution, you get the left side turns into the right side? Yeah. Which means that no matter what you plug in for x on the left and the right, you get the same thing. That's called an identity. That's not just an equation. That's just not equal. That's not just equal to each other. That's always equal to each other, no matter what. Because there's not a single x that's prevented from being in that domain. So anything, any real number you've ever encountered in your life that you plug in for x will be true, will make the same value on the left as it does the right. It's an identity. Example 4 is also an identity. By the way, example 3, that's an open sentence because only certain values of x make it true. Okay. But number 4, if you take a look at that, you've got x squared minus 1 over x plus 1. Think about that for just a minute. If you factored the numerator, because that's the difference of 2 squares, it would be x plus 1, x minus 1, and x plus 1 would cancel. Right? Which means you have x minus 1, which is equal to the right side. This is also an identity. However, it's not an identity for all real numbers. Because the left side does not equal the right side when x is negative 1. As a matter of fact, the left side is totally undefined when x is negative 1. The right side, when x is negative 1, is negative 2. We don't care about that. The left side is undefined at x equals negative 1. Do you see that? So we say in number 4, on number 4, it's an identity for all values of x except x equals negative 1. Okay? So its domain is restricted only by one number. But you have to be careful with that because it has to be true for the left side and the right side. Okay, some basic trig identities. These are ones that you've already been using as you did computations. For example, when you ran into cosecant, you wrote 1 over sine. That's an identity. They're reciprocals of each other. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Sine, if you start out with sine, is the reciprocal of cosecant. They're reciprocals. No matter which one you start with, you turn the other one over, you put 1 over its reciprocal buddy, and you get an identity. So there's actually 6 identities here that you've already been using. And the one that I've already told you about, and I can remind you how it comes about, is what we call the quotient identities. The tangent is equal to sine over cosine. And cotangent, of course, because it's tangent's reciprocal, is equal to cosine over sine. This all make good sense so far, based on the definitions you had? Do y'all remember why tangent is sine over cosine?
No.
Okay, I'll show you. The easiest angle to demonstrate this with is in the first quadrant, but we could do it in any quadrant so long as we paid attention to the signs, SIGNs. You with me? But I'm just going to do it in the first quadrant. If I open up any angle, I don't care what it is out here, and I know that might look like 60, but we're going to pretend it's more like 68 or 70. Okay, it doesn't matter. It's theta. And for this first part of the discussion, if I make this 1 like we usually do, which is on the unit circle, then this value right here is x, and this value is y. Because we don't know what that angle is. The cosine of theta is x over 1, which is x. Do you agree? The sine of theta is y over 1, or y, and the tangent of theta is y over x, which is sine over cosine.
Oh, okay.
Now, you might say, well, what happens if I don't have, what if I have something else besides a 1 here? Because then these turn into something else. Well, it still works out. Let's say that we made this 11. If I did that, made that 11, then this would have to be 11x and this would have to be 11y. Because if you make this 11 times longer, to stay in the same triangle that's similar to it, these are going to have to be 11 times longer. And so you would have 11x over 11, or still x. 11y over 11. Cancel these, you still have x and y, and the tangent is still sine over cosine no matter what theta is. And no matter what the size of the triangles are. Tangent is equal to sine over cosine every place cosine is defined. Where's cosine? I'm sorry. Cosine is defined everywhere. Every place cosine is not 0. That's what I should have said. Where's cosine 0?
90 degrees.
Cosine is 0. Think about your quadrantals. You guys got to get this in your head, or at least remember how to figure it out. Cosine is 0 or 1 only at a quadrantal angle. Sine is 0 or 1 only at quadrantal angles. Tangent is 0 or undefined or 1. No, 0 or undefined only at quadrantals. Tangent is 1 when it's pi fourths. But sine and cosine are only 0 or 1 on these special angles here. And it has to do with the point on the unit circle. That's the best way to do it. This is the point 1, 0. This is the point 0, 1. This is the point negative 1, 0. This is the point negative or 0, negative 1. And in all cases, as you've seen, the x value, the x right here, is related to cosine. Cosine is adjacent, so it's the horizontal one. Well, the horizontal value of this point right here is right here. So this is cosine sine. The cosine of 0 is 1. The cosine of, the sine of 0 is 0. Up here at pi halves, the cosine is 0 and the sine is 1. Over here, cosine, sine again because it's horizontal, vertical, and cosine, sine. So where is cosine 0? Yeah, straight up, straight down. The up and down one is where cosine is 0. And so we say that the tangent is equal to sine over cosine. It happens the 0 at pi halves, 3 pi halves, 5 pi halves, negative pi halves, negative 3 pi halves. X cannot be odd integer multiples of pi halves. That's where it's undefined. Those are the values. Those are the values of the angles that you cannot plug in here and get anything valid. That's where tangent's undefined. Tangent's undefined straight up and straight down simply because cosine is 0 there. That's why. You with me or not? Okay. based on those ideas right there, and you're okay with the cotangent being cosine over sine? Okay, now take a look at page 445, the exploration. Most of the time, explorations, I pick and choose which ones I want to do. This is a pretty good one. It's going to take some concentration on your part, so I need you to get your eyeballs on it. It's on page 445. In the middle of the page where you see the blue exploration box. Yeah, this is tricky, and what you're going to be doing is we're going to ask you questions out of the blue box, and you're going to have to look at the green box above it to try to figure it out. And it's going to take a little while, and you have to think really hard. And exploration one, number 1 says, theta is equal to 0. And, wait a minute, theta equals 0 is in the domain of validity. It's just in the domain of exactly 3 of those 8 basic functions. Which ones? 0 is in the domain. So maybe you want to look for ones where 0 is not in the domain and then list the others. And I'm going to take you through this first one, but then I'll kind of turn you loose on number 2 and 3. Try to figure it out for yourself. You can discuss it with each other if you want. But here's how we do number 1. It says we want to find out when theta, when the actual angle is 0, but the equation, both left and right side, are still defined there. Okay, what about cosecant? It's mostly about division by 0, so I'm going to look at the other side of that equation. Is the sine of 0, what's the sine of 0? What's the sine of 0? 0. So what I have is 1 over 0 on the right side. You see that? When theta is 0? So that was not 1. That 0 is not in the domain of that first identity. You see what I'm doing? Look at the next one. Mainly what you got to ask yourself is, what's the cosine of 0? We're letting theta be 0 all the way through this little exploration here in this first part. Cosine of 0 is what? 1. So we have 1 over 1. So secant and cosine are both, well, cosine is defined everywhere, but secant will be defined as 0. So that's one of them. You see that? Yes, no? Okay. Next one is tangent. What is the tangent of 0? We just learned it is sine over cosine. It is 0 over 1, which is 0. Tangent of 0 is 0, yeah or no? Got that? Which means the cotangent is not defined there because you would have a division by 0 and the reciprocal. So far, the only thing we've got is secant. Let's look at the next one. Sine and cosine are defined everywhere. It's not the left side of the equation I'm interested in. It's cosecant. What is the cosecant of 0? That's a tough one. It's undefined because secant is 1 over sine, right? And so you have 1 over 0 when theta is 0. So not only do we have possibility of division, we're always looking for division by 0, that particular denominator isn't even defined. So that's not one of them. When we plug 0 into that one, that identity turns out to be undefined. Look at the next one. What's the secant of 0? 1. So 1 over 1 is perfectly defined, and so we found another one. Cosine is another one that is okay at 0, when theta is 0. How about tangent? What's the cotangent of 0? No, the cotangent of 0 is, oh yeah, it is undefined. Yeah, it's not, okay, you're right. It's undefined. So we got another denominator of undefined. So far we've only found 2. So the other one's got to come from the quotient identities. What is, and again, the tangent is defined at 0, but is the other side its identity. What's the cosine? What's the cosine of 0? 1. So there's no division by 0 there. What's the sine of 0? Now we're considering the numerator. 0. But what's 0 over 1?
0.
Perfectly reasonable. So we found the third one. Secant, cosine, tangent. They are all defined when theta is 0. All the others are not. You see how this investigation goes? Okay, number 2 says, for exactly 2 of these 8, exactly 2 of these identities, one side of the equation is defined at x equals 0, and the other side is not. Which 2? That one's a little tougher. Do you remember when we got the denominator to be totally undefined because the denominator itself? The denominator wasn't 0. The denominator itself was undefined. Remember those two when we ran by it? They were sine and tangent, believe it or not. Those were where their denominators were not only not, that they're not, their denominators weren't zero, they weren't defined. That's what they're trying to ask us, kind of an obscure way of doing it. So I just did number 2 with you too. That's gonna be sine and tangent of that. Number 3, for exactly 3 of these functions, both sides of the equation are undefined when theta equals 0. Both sides are undefined when theta equals 0. Which 3? Cosecant is one of them. Cosecant is not defined when theta equals 0, and 1 over sine is not defined when theta equals 0. And that's precisely why cosecant is not defined there, because it is 1 over sine, which is not defined. Where's the next one?
Cotangent.
Cotangent, where is that? Oh, okay. Yeah. Tangent of 0 is 0, so 1 over 0 makes both of those sides undefined. Okay, what's another one?
Would it be cotangent in your quotient?
Yeah, cotangent and the quotient one fails too. Yeah. You will not be asked any test questions like this. It's just a really good idea and makes you think about these quadrantals especially, because these are the only places where sine and cosine take on a 0 or a 1 someplace, and you've got to remember where they are so you can decide if their reciprocals are defined or not. Okay, so every once in a while you'll run into a problem where you get the problem solved or you get an identity whittled down to nothing, and then it says, what is it when theta equals 0? You go, it's undefined. Crap, I did all that work and the whole thing was undefined. It'll happen once in a while, maybe. You got to keep in mind that not all of these domains, I mean, sine and cosine's domain is all real numbers. But that doesn't mean fractional combinations of them are. So be careful. It's all about these quadrantals. All right, Pythagorean identities. Let's see if we can work that out here. I'm gonna draw another clean picture here. And we're gonna see how Pythagoras can make our lives a little more complex. So I'm going to start out with that same triangle that I explained the tangent identity with. Make it a little bit different. If this is 1, and this is x, and this is y, then actually let's just call this r. No, I'll leave it 1. We'll deal with it. We'll make this something else in a few minutes, but let's just leave that at 1 for right now. So consider something else that you've been doing for probably since 6th grade. And that's Pythagorean theorem. In this particular triangle, isn't it true that x squared plus y squared equals 1? Isn't it also true that x is equal to the cosine of theta? And y is equal to the sine of theta? Is everybody convinced of that? All right then. That means that sine squared, even though I'm starting with that one, it doesn't matter because we're adding sine squared of theta plus cosine squared of theta equals 1 also. Yeah? This is the main identity that hardly anyone ever forgets. And if you know this one and can manipulate it even a little bit, it'll open you up to getting going on an ACT test. Probably not relevant for a lot of you now, but on an ACT test will take you from a 23 to a 27, just knowing this and how to manipulate it a little bit. Same. Okay. All right. So we all agree that this is the original Pythagorean identity, and we agreed that x and y equal these things, and so this is also true. And you go, but what if it's not 1? What if it's 11? Then again, this is 11, and so is this. This is 11, and so is this. Everything gets whatever that does, whatever multiplies by, everybody else does too. And so what I have now is, for Pythagoras, I have 11 cosine of theta squared plus 11 sine. I'm reversing the order because it doesn't matter. Usually you put sine first, but that's just convention. Equals 11 squared, right? Well, that means we got 121 cosine squared theta. That's this. By the way, this is shorthand for saying this, which is how you have to put it in your calculator. Calculator does not understand this shorthand, but it's a heck of a lot easier when we're writing to use that shorthand than write that every time. But when you want to when you want to write this in your calculator, you have to do the cosine of theta, close that parenthesis, put the whole thing in parentheses and square it. Because even if you did just this, that would square only the theta before it cosigned it. You with me? So writing it in your calculator takes a little extra effort. It's quite a bit of parentheses there, but writing it by hand, especially which is what we're going to be doing a lot of, this is a lot quicker and shorter. So I have 11 squared, I have cosine squared plus 121 sine squared in the squaring equals 121. And guess what? Cosine squared plus sine squared equals 1. It doesn't matter the size of the radius. It's always, always, always true that cosine squared plus sine squared equals 1. There's not even any domain restrictions because there's no chance to divide by 0, and both cosine and sine and their squares are defined everywhere. This is a nice one. There's no domain restrictions on this. So this is an identity that's defined everywhere. I'm going to write it right up here because I want to show you what I'm going to do. I'm going to manipulate these a little bit. Sine squared plus cosine squared, and I'm putting x in here. It means theta. That's an angle. Whenever it follows a sine or cosine, it means angle. It doesn't have to do with that x right there. Just get used to it. Whatever follows a sine or cosine is an angle. All right, so we agree that's an identity, or if you don't agree, you're going to have to come to an agreement because it is. If I were to divide each one of these by sine squared, is that a legal thing to do? Can I do that? If I divide every side by that? I just have to remember that if I'm going to do that, that now that I'm introducing division, I have to be careful what x is. X can't be where sine is 0. Sine is 0 at 0, pi, 2 pi, 3 pi, multiples of pi. But every place else is defined, so we'll go with where it's defined. That first one then turns into a 1. The next one turns into, think about this. If cotangent is cosine over sine, then cotangent squared is cosine over sine squared, because all you got to do is square both sides. So this is cotangent squared. And this is cosecant squared. That's another Pythagorean identity. But it's only defined where cotangent and cosecant are defined, and those places that they are not defined are where sine is 0. Okay. If I take that very same thing, the one that we like the best, it's defined everywhere, it's an easy thing to remember. Take that thing and divide everything by cosine squared. That's legal too, and it is defined everywhere that cosine is defined. This would be what? Tangent squared. This would be
1.
And this would be
Secant squared.
secant squared. So these are our 3 Pythagorean identities. I kind of destroyed that one. I'll put it back up here. This is the one everything stemmed from. These are the Pythagorean identities. And I will tell you the truth, and you can believe this or not, but it's true. I have never memorized these, never. Because I can do this in my head real fast. So if you can remember this one and what we did to generate these, we divided by sine squared all the way through in one place and cosine squared all the way through in the other. You can generate these if you forget them. These will not be provided for you on any cheat sheets. None of these, none of those 8 that we talked about, or these 3. These are expected for you to know. If you don't know these, you better remember how to get them from that one. Here's the interesting thing too. All of these things and their algebraic equivalents, you got to be aware of. For example, if you take sine squared plus cosine squared equals 1, this is what I'm talking about when I said if you can manipulate these a little, you can get points on the ACT test if you know just a little bit about what's going on. That is the Pythagorean identity, but so is this, and it's exactly the same one. That's easy, right? But most people, when they see this, go, I don't know what that is. It's cosine squared. It comes from this. This and all of its algebraic variations are all true. So when we're doing identities and stuff, if something shakes out like this, you go, I don't know what to replace that with. We replace it with cosine squared from this identity. And so, of course, it's always it's also true that sine squared is equal to 1 minus cosine squared. So what I'm saying is, you need to know this, but you also need to be able to recognize its algebraic equivalence. Same thing with this. Quite often you'll see 1 is equal to cosecant squared minus cotangent squared. I have to come back to this and know that. Or you might say cotangent squared is equal to cosecant squared minus 1. You need to know these and their variations. One thing I have memorized is that these two cofunctions, they're together in the same identity. I can just never remember where things fit. I just have to do it in my head. But these two cofunctions go together and these two non-cofunctions go together. And then there's one of each up here. A sine and a cos. A little bit of memory things there. Okay. So far we've gotten 11 identities. They are listed in the green box at the top of page 445 and the green box at the top of page 446. If you want to use those as a crutch for a few problems that you do today, fine. But by the time you get done with this exercise 5.1, you better have them memorized and be able to use them. All 11 identities. No cheat sheets for these. These are important ones. Okay. Example 1 says, find sine and cosine of theta if the tangent of theta is 5 and in a quadrant where the cosine of theta is also positive. So here's what you're doing. In example 1, we're taking the given information, which is given last, and it says, if the tangent of theta is 5 and the cosine of theta is also positive, that places us in the first quadrant, because that's the only place where tangent, which is 5, is positive, and cosine is also positive. And by the way, when you read that, you do not read it like this. This is how you would read it. Like I've told you this before. This is how you would read it if you were learning to read in kindergarten, first grade. You would say, find the sine of theta and the cosine of theta if the tangent of theta is 5 and the cosine of theta is greater than 0. When you become fluent, you will say, find sine and cosine, yes, but in a quadrant where tangent is positive and so is cosine. That's how you read that. That means we're in first quadrant. So what we have to do is go in, that last bit of information tells us which quadrant to be in. It's very definitive. It's the first one. There's no other option. And we draw it in such a way that the tangent is 5. Tangent is opposite over adjacent, right? So this thing ought to be a pretty tall triangle. So that 5 comes out 5 over 1. You know what I'm saying? Yeah, no? And Andrew? Yeah, tall triangle. So that the opposite side is 5 times bigger than the adjacent side. So it's going to be tall. Put a 5 here and a 1 here. And Pythagoras says that this is the square root of 26. Okay? We don't know what theta is. We don't care what theta is. We want the sine and cosine of theta. We don't care what theta is, just the sine and cosine of it. So now that we've drawn this and Pythagoras told us the third side, we say the sine of theta is equal to 5 over root 26. And the cosine of theta is equal to 1 over root 26. Does the author rationalize those denominators? He does not, so you're going to be able to get away with it too. That's fine. Rationalizing denominators at this level of math is stupid, especially with the calculator. Okay, so don't let you leave it like that. If you are uncomfortable with that because you've always rationalized, then please rationalize. 5 root 26 over 26. Root 26 over 26 is fine with me, but I'm not going to require it. Okay, the only thing I'm going to continue to require that you do arithmetically is reduce fractions as far as possible and simplify radicals. 26 is 13 times 2. It's not going to simplify. If you had root 8, I expect that to be 2 root 2. Okay, but you can leave radicals in the denominator if you like. Okay, here's an interesting thing about, I think I've told you this before, probably in geometry, but I'm sure you forgot because it was really hard for your mind to grab onto at first anyway. If you have just a plain old right triangle, not in any particular quadrant or anything, so we're going back to geometry for a minute here, and you have, we'll put the C here, that would be a little c here, put the A up here, it doesn't have to be that way. Little b here, little a here. Then, this is really super easy, what is the sine of A? Good. What is the cosine of B? And how are angle A and angle B related to each other?
They both add up to equal 90.
Yeah, they have to equal 90, which means in geometry we call that complementary. Didn't we? When angles add up to 90, you see that regardless of the triangle I draw here, if this is a right angle, that these two have to be complements, right? And see, can you see that the sine of A is equal to something here, and the cosine of B is equal to that same something? So listen to this statement and see if you can understand it. The sine of an angle is equal to the cosine of its complement. That's what this stands for. It does not stand for co like co-captain or co-president or co-something. It stands for complement. That's what co stands for. And co in any, on the front of any of these guys that you've seen. I mean, we got cosecant, cotangent, and cosine. We have cofunctions that belong to all of them, and that's always the case. I want you to look at the bottom of page 446, where it says cofunction identities. And I want you to look, for example, see the sine of A? At the very first thing you see there when we're talking about angle A? Sine of A? Now go find the cosine of B. Same thing, right? Y over R. Now, look at the tangent of A. What's the cotangent of B? Y over X. That's what co stands for. Look at the secant of A. What's the cosecant of B? Same thing, R over X. Now, if we do the cofunctions of A, look at the cosine of A. What is the complement of A? B. So now go find the sine of B. Cosine of A is X over R, sine of B is X over R. So I think I've drilled that into you hard enough. The co part of these words means complement of the thing it's coing. Cosecant is the complement. If you take the complementary angle, you get the same thing as the secant. Related. Anyway. Now, that's just a reason why we call them co-functions. So since okay, let's take this let's do just a little more. I could say that angle B is equal to pi halves minus A. Couldn't I? If I'm going with radians, pi halves is 90 degrees. So angle B is equal to 90 degrees minus whatever A is, right? And angle A is equal to pi halves minus B, right? Which means that, now see if you can make this leap, which means that the cosine of A is equal to pi halves times the sine of A, because pi halves minus A. Did I already say that? Let me see. No, it's the sine, yeah. So the cosine of A is equal to the sine of pi halves minus A. Okay, so what we're saying here is that the cosine of A is equal to the sine of its complement, but I'm writing the complement in terms of A. Okay? Okay, then the top page, on page 447, shows all of those things and how they're related. All the cofunctions go together. The sine of pi halves minus theta is equal to the cosine of theta because pi halves minus theta and theta are complements. I'm at the top of page 447. Are you there? Okay. So the cosine of pi halves minus theta is equal to the sine of theta. It doesn't matter which side they're on as long as sine and cosine are co together. Same thing with tangent and cotangent, secant and cosecant. So we're going to bring all this together here in just a minute. But there's one other discussion we got to have. We've had this discussion in algebra, but now we're going to apply it to trigonometry, and that is which functions are odd and even. I alluded to this the other day. We did a little bit of stuff with this the other day, and I think it went right over a lot of you. You didn't realize that it was important. It is. Do you remember how to recognize graphically an even and an odd function? Evens do what? Yeah. Even the functions reflect over the y. Odd functions reflect over the origin. In other words, what happens in the first quadrant kind of happens in the second or the third quadrant, and it has to go through the origin, right? So let's take a look at a brief graph of each of these things. If I have the sine of x, and I'm going to graph that thing, it looks like this, right? But if I continued, it would look like that, right? Cosine looks like this. I'll draw it a little bit better this time so I don't have to run into things. Cosine looks like this, but it also continues back here, yeah? And the tangent looks like this. First branch of it goes like that. All the others do the same thing. Which one of these things, are any of them even? Cosine is even because it's reflects over the y-axis. What about sine? Is it odd or even or neither?
Odd.
Odd. Because right here you can see, right there, it's going to reflect. Even this piece over here will reflect over here, right through the quadrant this way. So this is odd. How about tangent?
Odd.
Odd. Now let's remind ourselves what that means algebraically. Even and odd functions have this property. Even functions have this property, actually. If a function is even, and we're talking about functions in general here, if it's even, it has this property, that f of x is equal to f of negative x. Because the classic even function is a parabola, and if you take 2, you get up to here. If you take 2 or negative 2, the opposite of it, it also has the same value. That's what reflection over the y means. You following? Okay, so that's a property of evens. This is the property of odds. This is how they are defined. Negative f of x equals f of negative x. That was a little harder to determine, but the classic odd function is, and I'm going to exaggerate it a little bit, is the cubed function. And this one says if you go to 2, you get up here to 8. But this one says if you go to negative 2 over here, you have to go down to the opposite of that. That's classic odd function. See what's going on? If I take f of 2, I get 8. If I take f of negative 2, I get negative 8. Okay. So when I learned this, my teacher didn't take he took the time and I wasn't paying attention, or I didn't understand what he was saying, or what I'm saying is for survival mode, even functions, this just disappeared somehow. For odd functions, it migrated out to the front, but I didn't lose it. You can memorize it that way too if you want. Now, all of those things in the cofunction identities, these 2 green boxes on here are going to help us to get example 2 done. Example 2 says if cosine of theta is equal to 0.34, find the sine of theta minus pi halves. Whoa, that seems like a tall order. The cosine of theta is equal to 0.34. What I want to find is the sine of theta minus pi halves. Now here's a problem. The cofunction identities, if you'll look at the top, are not phrased this way. They're pi halves minus theta, not theta minus pi halves. And so I can't use that directly. But you need to remember this, and I will go into greater detail here if you can't remember this, but this could be written, if this doesn't make sense to you, let me know. Could be written as negative theta plus pi halves, plus pi halves. Couldn't it? Which means that now that I got a plus sign there, I could write it like this if I wanted to. Negative pi halves minus theta. Right? But sine is odd. I have this situation. I could write it like this because sine is odd. See the negative inside? I'm going to let it migrate to the outside, and I have negative sine of pi halves minus theta. Now I've got a cofunction identity, which is cosine of theta, right? Because I've got this in the right order now. I was able to turn it around by factoring out a negative. Negative is now there, but I'm saying I have an identity for this. It's the sine. I'm sorry, cosine. This right here is the same thing as the cosine of theta, isn't it? But it's negative. So the answer is negative 0.34. So that required even and odd functions right here. It also required cofunction identities, but we've got to realize that that's in the wrong order. So when you change the order, you factor out a negative, and if the thing you're working with is an odd function, it comes out to here. What would have happened if I'd have said, let's do this one. What if I'd have said the sine of theta is equal to 0.34 instead. That's what I'm gonna start with, and I want to find the cosine of theta minus pi halves. Do you all see that this one right here is the same thing as the cosine of negative pi halves minus theta?
Yes.
And because cosine is even, do you see I really have just that? Even when it disappears. And so I have the cosine of this, which is equal to sine, so this one is 0.34. It's the same thing. There's a lot of gymnastics, so to speak, there, doing this. Are you okay with that? See what's going on? It's gonna take some work, it's gonna take some effort. All right, a couple more things. I've got to do 3 more examples, and then we'll be done with this section. We're going to take those identities, the 11 identities that you had, and we're going to start using them to rewrite, meaning replace certain expressions with ones they're equal to because they are identities. This is going to require a lot of memory of algebra, things we do algebraically. Okay, let's try example 3. It says, simplify the expression. Sine cubed plus sine cosine squared. Okay, we're to simplify that expression. A lot of times simplifying requires factoring. That's what's required here. What do we take out? A sine. What's left? You all see that's what's left when we take a sine out of both terms? You good? Well, that's sine. Why? Because that's 1. That's your identity application. Sine squared plus cosine squared, which is left on the inside. That's 1. Cosine x, just sine x. Okay, the next expression we're going to simplify is cosecant x plus 1 times cosecant x minus 1 over sine squared. Talk about throwing you in the deep end. I think I just copied that. I think this is cosecant. This is secant. I was going to say, I'm not sure how I'm going to proceed here. I have no idea what I'm going to do with that. That's what they have. So in this case, it's not factoring, it's FOILing or multiplying it out. What do I get if I multiply the numerator, the 2 binomials in the numerator? What do I get? Plus?
Oh, minus 1.
Minus 1. These are conjugate pairs, so they will multiply out to be a difference of 2 squares. We good on that? Okay, over sine. This is a Pythagorean identity, one of the algebraic versions of it. And if you look carefully at it and manipulate it, this is tangent, is that right?
Yeah.
Okay, so I'll go right down here. Tangent squared x over sine squared x. Now we're going to go to the reciprocal identities. Rename tangent in terms of sine and cosine. So if I come up here to continue that, I would rename the tangent as sine squared over cosine squared over sine squared over 1. That's what I'm doing. Renaming all of this stuff so that I've got a fraction over a fraction. To remind myself that I need to tip the other one up. So it's going to be sine squared over cosine squared equals 1 over sine squared. And I get to lose those in the canceling. I'm sorry, not equals, times. And so I end up with 1 over cosine squared, but that is secant squared.
I hate this so much.
A lot of algebra, a lot of identities. Algebra here, because you got to FOIL it. Here is an identity, you got to recognize it. So you replace it with this, you go, crap, I still don't know what to do with that. So you rename tangent in terms of sine and cosine. which makes a complex fraction. You turn the denominator over, cancel what you can, you still got a reciprocal identity. It's a lot of work. It's a lot of stuff to recognize and know. One more example like that. And I don't have enough board space up here, so I'm going to erase these just a minute. Okay, we got cosine over 1 minus sine. Minus sine over cosine. Okay, now this little skill I'm about to show you here is going to be used over and over and over and over again. And if you were never very good at doing fractional arithmetic in algebra 2, you will get good at it here or die. Because you have to know what you're doing. In order to get these two, and always when we're trying to subtract or add, almost exclusively, we want to get them together into a single fraction to see what's going on, see what we can do with that. Single fractions are way easier to handle than sums and differences of fractions. So the objective here is to find a common denominator and subtract. And the common denominator is cosine x and 1 minus sine x. They don't share a thing in common, so it takes both of them to make the common denominator. Which means that I'm going to need to multiply this one by cosine over cosine, and this one by 1 minus sine over 1 minus sine. And since there's two terms in here, it would be wise of you to put parentheses around those because we're going to have some distributing to do. You following everybody? Yeah. And when I get done doing that multiplying of these things, what's going to happen is they're both going to have this for a denominator. Both of them will have this, right? Which means that all I really need to do is deal with the numerators. This cosine times this cosine is cosine squared. That minus belongs right there. And then I've got to multiply this through there, and that's going to be, I'm going to leave that minus right here. I'll deal with that in just a minute. So pretend that I'm not dealing with this right now. So it's really sine I'm distributing, not negative sign, okay? Don't use that negative twice. I'm going to do that in a minute. This will be minus all of that distribution, which is sine x plus sine squared x. Oh, yeah. Thank you. Minus, because I haven't dealt with the negative yet. I was doing that already. Okay, so to save myself a line, is it okay if I do distribute now?
Yeah.
Like that? You could do it as you went through. I mean, you could distribute a negative sign through there and get this. Handle it, no problem. Oh, and look what we have. 1 minus sine. Do you see it? You do? Over cosine times 1 minus sine. That's 1 over cosine. And that's secant. I can see the stress in Sarah's aura. Okay? That's where this one ends, but that's the kind of thing you're going to get all these identities to look at. And by the way, on the next test, I will be, if necessary, I don't think it will be, but I will provide you with the cofunction and the odd and even identities if you want me to on page. But the basic trig identities, there's 8 of them, and the Pythagoreans, nope. You will never get a cheat sheet for those. But the others that we run into, I will give you access to those. Print off the page and give it to you. What?
Which ones are those? That we get the,
The ones you have to know,
what are the ones we get the cheat sheet for?
starting with the cofunction identities on page 447.
Okay.
I will provide those and the odd and even identities that you see there, and any other identities that come along in this chapter. But the basic ones and the Pythagoreans you have to know cold. Okay? All right, that's it for today.
Can we do 5.1 A and B today?
No, we just did the A part.
Okay.